Hello friends. So finally we are going to look into some hands-on example using Python around linear regression, and we will primarily use the library called as Scikit Learn, which is a machine learning library, and it offers various features which include classification, regression, clustering, dimensionality reduction, model selection, pre-processing, and so on. So right now we would be focusing primarily on regression. In next videos we'll talk about model selection as well as dimensionality reduction, and then in some non-supervised learning we'll talk about clustering, and for supervised classification we will look into examples of supervised clustering using support vector machines, nearest neighbors, and so on. And pre-processing would be done wherever required. So in nutshell, we will be learning all these 6 features in our various videos, and that will complete the compendium of machine learning. So the interface that you see here is called as a Jupyter Notebook. If you are new to Python or have never used Jupyter Notebook, I have prepared a very small 50-page manual which will enable you to install Python on your machine, be it Windows or be it MacBook, and you should be able to install various packages once you go through that particular module. Also, if you are not able to install Python on your machine for some reason, Google offers this Google Collab. So all you have to search is Google Collab, and leave this, and if you go to Google Collab, you see here you can create your own notebooks, or you can also get a similar interface without doing any installation on your machine. Here this is my interface which I was using to prepare this tutorial, and you should be able to create even a new empty notebook that I would be using for this particular tutorial. Now in this tutorial, as I mentioned, we will look at the examples of linear regression using scikit-learn, and we will demonstrate application of regression on some toy data or synthetic data that we'll generate ourselves, and we will also perform multivariate linear regression using some real data. And thanks for our friends at MIT who has provided us this data set through MIT courseware, where we would be setting up this multivariate linear regression on a climate change problem. You can also download the dataset from my GitHub page. Again, link is in description. And I will also share this notebook with you through my GitHub, but I strongly recommend that you write each and every line yourself, because practice definitely makes you good when it comes to programming. And so with that, we will begin. So we will be using 3 prime libraries here, and these libraries that we are going to use are NumPy. So we'll import NumPy, and we will use some alias or nickname as NP. Of course, we are going to do regression using scikit-learn. Scikit-learn goes by the name sklearn linear model, and import linear regression, because we would be using linear regression from this. And in case you have not installed any of these libraries, all you can do, if you have installed Jupyter using Conda, all you have to do, Conda install NumPy, and yes, so that it does not ask for any input. So if you do that and press Shift plus Enter, so Shift plus Enter will execute that particular code block, and that particular package would be installed on your machine. Now in my case, I have already installed all these packages, so let's see that how this ends up. Okay, so now we would be doing this import NumPy, import sklearn, and linear regression. And so it says that it already exists, and now it is downloading some, so let it complete. So I will be doing this code in real time, so you have to bear with me if we go slow in certain portions. Okay, now it is installed, but you know that you have to only install one package once. So once you have installed a package, that would be there forever until you uninstall Python or get a new machine, and so on. Another thing is that we want our plots to be produced in line. So there is some special function which we call as matplotlib inline. So this is sort of housekeeping that we do when we write Python script. So you can always include that whenever you are working in Jupyter Notebook, so that our codes are produced, our plots are produced as we are moving. Alright, so here we will set up a regression problem. So we will generate x from numpy, a range. Uh, generate uniform samples of x between 3 and 70 or continuous samples. So I will execute this. Oops, this should be from. Alright, so now if I print x, let's see what this x look like. Okay, so x is an array here. You see that it has number all the way from 3 to 69. Now since this is a toy data, I want to generate a y which I know that it is a linear function of x, but I will generate it in a way that is, it should be, I want to have an equation which looks like x equal to y equal to x times theta plus some random noise which is coming from normal distribution and with some mean of 0 and variance of 10, and I want this to be as good as length of x. So I want to generate n samples and where n is the length of x, and that should be my y. So I want this to be governing equation. Now to write this in Python, now you can see that now x is a vector, theta is just a number, and if we take a dot product between them or a matrix we do a matrix multiplication of k cross 1, because the size of x would be k cross 1, which you can check from x dot shape. So it is 67 cross, so it is not able to identify that dimension. So what we will do, we will reshape. So we want x to be vector, so we will say that x dot reshape. I don't know how many rows would be there, but I am sure that how many columns I want. So the syntax is, you say -1 comma 1, and now if you do x shape again, you see that it has been changed to a row a column vector which is of size 67 rows times 1 column. Now let us generate y. As I said, we want to generate y as product of theta and x, and I will take the dot product, in this case x between x and some parameter of my choice. Since I am interested in univariate regression, I will just do np array. It's a 1 cross 1 array, or it's just a scalar in fact, but for generalization I am doing the matrix multiplication so that you can also extend this to a problem of multivariate regression. And I will add some noise which can be generated from np.random.normal, and I will use mean of 0, variance of 10, and I will have length equivalent to x, and let us see that what my y looks like. So this is my y, and I have also generated x. Now let us see that without doing any regression, how this y is dependent upon x, and we will generate a linear plot between y and x. To do that, we use another library which we call as matplotlib.pyplot, which help us to plot. So we will do import matplotlib.pyplot as plt. So again, these alias are used to give nicknames, otherwise you have to type this complete syntax again and again. So we just call this as plt. We will run this again, and we will run this again, and now we will do plotting between x and y. So all you have to do is plt dot plot. Within plt module there is a function called as plot, and we will plot x versus y, and we want a scatter plot. So our scatter plot looks like that. So here you can also change colors, and if you want to make it red, that's totally fine. So we will get it as a red scatter plot. Now one thing is clear, that between x-axis and y-axis there exists some linear relationship, and we know because we have synthetically generated this y, but we want to fit a generalized linear model or a straight line that best describes this data. Now we have already learned that how to tell the coefficients, how many coefficients should be there, or what should be the value of coefficient using pen and paper using maximum likelihood approach or OLS and so on. But here we will let the computer do that. So what we will do is that we will use something called as regression between X and Y. So the easiest way to do is, all you have to do is create another variable in which we will store our results of regression. So regression would be linear regression. Make sure that you pay attention to what letter you are typing in small block or in caps with caps lock on, because Python is very sensitive to uh, it, to whether it's a small scale small letter or it's a capital letter. Now regression coming from linear regression. Within linear regression, all we will do is that fit the linear regression between X and Y, and let us see that what we get. So now when this empty bracket changes to a number, that means code block has been executed successfully. Now if this is done, let us see that what are the parameters we have gotten. So we will do reg dot coefficient, and we got that the slope that it identified is 1.3745, which is closer to what we said. It is 1.5, but we also added some noise, and this noise plus there would be some intercept that regression will automatically identify. So if we see that what is the value of intercept, so we see that value of intercept is 4.5 and coefficient is 1.37, which is very close to what we provided. Now let us also try to visualize that how this best fit lines look onto our plot. So what we will do, we'll plot this again. So we'll plot this again, and here what we will do, we will do plot plt.plot x and versus x. Let us plot the predicted values of y that is identified using the regression of scikit learn. So what we will do, np.dot x comma regression dot coefficient underscore, because these are the coefficients, and I have to also add the intercept. Now if you see here, I am doing nothing. If I write in plain language, I am saying plot the curve with x on x-axis and y is equal to mx plus c on y-axis, and I want this as a line plot. And you see that as soon as I press shift plus enter, I run this code and I see that this is the best fit line predicted by my regression class using scikit-learn, which is pretty neat. I mean, this is a good generalized model. It is not any all over the place, passing more or less through the center of this particular scatter plot. And we will look into that, how to check whether quality of plot is good or not. There is something called as a regression score. We will have a dedicated video on score. So what we will do, tell me the score, how good my model is on predicting y if I give input as x, and you see that my regression score in this case is as high as 0.9. So 1 being the best, 0.9 is the percentage of variance that is being explained by model. So I would say that this is pretty good model. Alright, so this is a simple case with linear regression. If you want to play with this, you can even create some polynomial data. Let us say that we create this as raised to power 4. That is now x is a raised to x is equal to alpha times y to the power 4. And now we try to see this, that how our data looks like. Again we do some regression and let's see that how it looks like. Now you can imagine that, see, our data now is being generated using a function of order 4, and we are trying to fit a straight line, and of course the fit should not be that great, and here we get the regression score much lower than what we observed in the previous case. So you can play with this toy data to internalize these concepts of linear regression. And with this, let us move to a real world example, which I mentioned, a climate change data set. So in my working directory, I have a file. So you should read little bit about working directories. I will post a link in description if you want to change working directories. So I already have this file in my directory from where I have started this Jupyter notebook, which I call as climatechange.csv. So if you type ls and you see this particular file is present in your working directory, you would be good to go. I will be importing this climate change.csv, and this is a CSV file, or in layman language in simple Excel file, which I will import using pandas. Pandas are amazing, absolutely elegant way to handle CSV files in Python. So what I will do, I will create a variable called as df data frame, in which I will read the CSV file with name climate change.csv, and when I run that, I see that this df has been imported, which include year, month, some variables some greenhouse gases concentration all the way from 1983 to 2008, and there is something called as temperature here. And in this case, our task would be to predict temperature given the concentration of various greenhouse gases. All right, so this would be a task here. I will make it a little nice. So all right, okay, so this would be a task with real data, which we will be using on data frame. Now if this is clear, let us get started. So first of all, let us do it as a univariate regression problem. I will use x as pd dot data frame, or I will just import carbon dioxide concentration, and I am assuming that temperature or global average temperature and just depends on the carbon dioxide. This would be my x would be carbon dioxide. So in data frame there is a column called CO2, and I will assume my y just depends on and my y is temperature, that is temperature is dependent on carbon dioxide, and I want to predict y. All right, so I have divided this x, I have named this x and y. Now there is something called as the concept of testing and training in data. So training means that you give some samples n and you set up the model where you learn this particular model, and in testing you try to predict on the surprise data sets so that your model is generalizable enough and it is able to predict the values that it has never seen before. Again, we will talk about these thumb rules when we talk about improving our machine learning models, but right now let us say that x test train, we take first 214, there are 308 samples here. So out of that we will use around 70% for testing, for training, and 30% for testing. So we will say that x train is x0 to 214, y train is equal to y0 to 214. Similarly, we will say x test equal to x everything from 214 to the end, and y test is equal to y 214 towards the end. So if this is the case, we run this. Now we have created x train, and I will also print y train. If we have done that, we see that here the length is 240, absolutely right. Similarly, you can quickly check what is the length of x test and y test. Again, this is the length is 94, so we have divided our data set into training and testing. Now we will fit our model on training data and we will make a prediction of test data. Again, we are not making any assumption or any bias about the data. I have not even seen or plotted this data, but I am just going with some physical understanding that as the concentration of greenhouse gases increase, my temperature or global average temperature anomalies with respect to some benchmark period should increase. Alright, so if this is clear, let us start looking into some scatter plot first. That is, global temperature really depends on carbon dioxide, and we will not touch the test data. We will just focus on train data for now. So what we'll do, we will create a plot of some size. We want our plot to be a little bigger so that we can see it. And these are some, again, taking care of cosmetics. That is, we want to set up our labels or size of labels to be bigger and bolder so that all of us can see. What we will do, we'll just plot x training data versus y training data, and you clearly see indeed there is some linear relationship, at least for training period, between temperature on y-axis, or this is temperature anomaly, that is difference with respect to some benchmark period, and on x-axis we have the concentration of carbon dioxide. And you clearly see that for testing period it would not be a bad idea to start with a linear regression. Alright, so we will also add some labels so that our plot is nice and easy to see. So now I've added, this is carbon dioxide in parts per million. I should also add in ppm, and this is global temperature and anomaly. Alright, now if you see that I have updated this. Similarly, I can also add title here. So one important thing, if you are new to programming, do not take anything for granted. That is, make sure that you add labels nicely and your fonts are legible. Otherwise, it becomes a habit to write shabby codes. Alright, so let's move to our regression. Now what we will do, we want to fit a relationship between X train and Y train, and all we have to do is what we did in previous case, regression. Now I will create a new variable, regression, and I will do a linear regression between and linear regression dot fit X train and Y train, and I should be good to go. Okay, I got some error. It says that you have to reshape the data set. Okay, so that's fine. We will reshape this data set, and in this case, all I will do, I will change this to data frame. All right, here you go. So all I have done is that it the same problem that it was not it we when we are doing taking the data frame, the size consistency should be preserved. So what we do here, that we import this as a PD data frame df or PD data frame df, so that both of these are read as vectors of known shape. Because when you just import it as df, then it loses its shape and hence it gives some shape error. So there is a minus change that we make here. All right. So then now we are settled with regression, and now let us do some plotting, that how our fit looks like. Ax dot plot x train np dot x train regression coefficient plus regression intercept. Again the same thing. I am plotting x versus mx plus c with some line width 8, and you see that for training period this is the best fit line that we have estimated using this data, and it's not a bad fit. Now this is not the end. We have trained our model. We have to test this model on some of the data sets that it has not seen previously. That is why we created this test data separately, and we will do some prediction here. To do that prediction, so we will use predict function. So now we know this regression dot predict, and what we will do here is we have some test data, and this is our prediction of test. Now let us try to plot this on our data set and see that how it really looks. So what we will do is, since this is a univariate regression, we can simply go here and again do that ax plot x test versus np dot x test, whatever regression coefficient we have determined, plus the intercept that we have, and we will plot them in red color to make sure that they are different from our previous color. So we'll say that this is equal to red. Now if you see here, this is our prediction, and now we will also plot the actual data. What was the actual data here? And we will say that this is equal to x test versus y test color, and we will give some yellow color here, or violet. Violet is better. Okay, so you see that something changed here, that in testing period our model is not performing well. Temperature was increasing up to certain point, and after that for certain period there is a decline in this temperature, and this particular thing is not captured by the regression because we are dealing with a linear regression which will keep on increasing monotonically, because when we were training we saw there was a trend. However, in testing there was some reversal of a trend, and actually there was some pause and then there was some reversal. And interesting thing is, this period in climate science is known as the period of hiatus, that there was a brief pause in global warming, and this period started in later half or towards the late 20th century, and it's visible that whatever trend we learned is does not generalize here. So this also highlights the importance of why we have to consider training data and testing data separately, so that we just don't get complacent that okay, we have learned data on some generalizable pattern and how it should perform on the surprise model. So one thing is for sure, that this univariate regression, while performing very well on for training, and you can test it. So what we can do, we can always predict the score, that what was our score when we were training this model. So all we will do here, again I'll just remove this. Regression score for training was around 0.425, and same score for testing comes out to be, I'm sure this would come out to be negative, and yes, it is minus 1.24, showing that the performance on testing is not that great, and hence this is not a good model to begin with. Okay, so if this is clear, we are done with our first example of univariate regression, and in next video we will consider the case of multivariate regression using same dataset.